So today I want to talk about domain walls and cosmic strings, which is the broader field of my PhD thesis. So let's start with, oh, didn't connect properly. Okay, let's do it like this. Now before it was working. I don't know where. Okay, so, okay, from the beginning. I want to talk about domain walls and cosmic strings, which is the field of my research in my PhD. So let's start about talking about the aim of this talk. First of all, the most important thing I want you to understand is what exactly are domain walls and cosmic strings. Then what might also be interesting for you is why are we even interested in them? And lastly, how do we find out more about them? So this means how is research handling them right now? So it's three basic questions: what, why, and how. Let's start with why. So high energy physics models, like for example, the grand unified theories, they predict symmetry breakings to take place. You already heard about this in the lectures, I think yesterday. And this happens during the early stages of the universe. These symmetry breakings can create topological defects. And domain walls and cosmic strings are certain types of topological defects. So this means if we observe domain walls and cosmic strings, we obtain a direct link to the early universe, which is great because it is analogous to fossils and paleontology. So paleontologists, they search for fossils for finding out more about the early history of the Earth. And we are trying to do similar things about the early history of the universe. And then the difference is that we first need to find out what exactly we're looking for. It's not like they're just lying around somewhere. Because what kind of defects form also depends on the underlying theory. So yeah, basically we can constrain theories by possible observations or by possible simulations, which we are doing. So in the end, this means for learning, one way of learning more about the early universe is by understanding what exactly are topological defects, and also how can we make the connection to nowadays observations. Since they formed a long time ago, the evolution in time is very important to understand for knowing what we are looking for today. So perhaps you already know this example with the table. Yeah, it was yesterday, I think, in the lectures. This is just a very basic example of what a topological defect is. It's not yet connected to the correct physics, but let's make a recap of it, although you have perhaps already heard of it. So you can imagine you have a very big table, and for every person, there's exactly one plate and one fork. And the forks are just in between the plates. Now, if somebody wants to start eating, this person needs a fork. But which fork this person takes, the left or the right one, it's completely random, the choice. Like there's no reason why you should take one or the other. So the first person might start to eat and take the fork to the right of the plate. And then naturally, all people in his surrounding will do exactly the same, because that's the only logical thing to do in this case. However, this table is extremely big. So on the other side of the table, they don't see what's going on. So they might choose the fork which is on the left of the plate. And then also there in the surrounding area, everybody will take the fork which is on the left. And at some point, these two groups will meet. So this means there will be one person without any fork or one person with two forks. And this means we have a symmetry breaking, and this is a topological defect in the end. Now, how can we combine this with physics? Of course, in physics, it's a bit more complicated. For that, first, we need to understand what a potential is. You probably already heard about it, but still I want to do a very short recap of it. And you just keep this table example in your head. So what is a potential? Basically, you can imagine it to be a simple landscape with hills and valleys. So here on the x-axis, on the x-axis, we have the position in space. And on the y-axis, we have the potential energy, which correlates to the height of the hills and valleys. So this means when we have balls rolling in this landscape, when they're up here, they have high potential energy because they are also high in altitude, but these balls will inevitably roll down because the stable regions are the valleys. There's also one unstable peak here, which is right on the top of the hill, but still we expect most balls after some relaxation time to all settle in those two valleys here. So this is the basic idea of the potential. Objects roll from high to low potential and stay in the valleys. Now, in our case, it is a bit more abstract. So now we have a field, phi, with a potential v of phi. And now the hills and valleys are not in space, but in terms of field values. And then the shape of the potential tells us whether the system is stable and how it might change over time. So what does this mean that they're field values? We can imagine it like this. So except of the spatial axis here, we have the field axis phi here. And now let's assume the two minima are at +1 and -1. Now this means that, for example, in this auditorium, we have a lot of different places in space. And for every single place in space, for example, for every chair that we have here in the auditorium, you have to choose one value of phi. And after some time, you will know that it settles at either -1 or +1, because these are the minima. So if we just look at the chairs, there will be one chair with +1, one with -1, and so on. So it will settle at these values. So this potential here just tells us what values are most likely to be found in space, because these are the minima. So how can we connect this to our topological defects? We start with the easier example, which are domain walls. We have here again the x-axis phi and the potential v of phi. We assume that very early in the early history of the universe, we have a potential which looks like this. It's like a simple parabola. It's very easy. So we know that everywhere in space, we have the field value phi equals 0, because this is the only minimum. However, the universe was expanding, or is still expanding, and this means that the temperature drops. And when the temperature drops, the potential shape can change. So afterwards, it might look exactly like this for the case of domain walls. So this is called a phase transition, because the potential changes its shape. And this can be related to the table example with the process of choosing a fork, because now all the balls which were here in the minimum have to choose. Do they choose the right or the left minimum? And this can happen everywhere in space, randomly. However, like in the table example, areas that are close to each other will always choose to be in the same minimum. So you will have patches of area where where everything is at phi positive minimum, or other patches at the negative minimum. So when we look at this, I'm sorry that this doesn't have a lot of pixels, this picture. When we look at this in space, we can see patches where it's in the positive minimum, patches where it is in the negative minimum, and so on. And now between these two regions, there are topological defects, which in this case are called domain walls, because they are walls which separate different domains. So it's kind of self-explanatory. Now let's take a closer look at what exactly is happening with the field. Here on the left, you see again the potential, like before. We set to be the positive and negative minimum at + and -1, which is an arbitrary choice. It can be anywhere, but let's just assume + and -1 because it's easy. Then this one here, this plot, shows on the x-axis a spatial dimension. So if we look down here, you see that for a very long distance, the field is always at -1, because in this whole area here, the field settled at this negative minimum. And another area of space here, it's always constantly at +1, because it's settled here at the positive minimum. However, between that, it has to interpolate continuously. So this means at some point, which is exactly where the domain wall is, the field has to jump over the maximum. And this results in a higher energy density. So you can see here, while the field is in one of the minima, it is constantly at energy density equals 0, which is here the orange line. And here again, but at the domain wall, at here x equals 0, you have a very high energy density peak. So this means domain walls are areas where we have a higher energy density. Now, since you now hopefully understand the concept of the domain walls, we can go on to the cosmic strings, which are also topological defect, but slightly more complicated. The idea is basically the same. The main difference is that the potential has a different shape. So here it is three-dimensional, as you can see, and not only two-dimensional. So we can see here on the left the potential before phase transition. So table example before people choose their forks. You can see it. There's just one minimum. So everywhere in space, the value will be phi equals 0. But after the phase transition, we will have this potential here, which we call Mexican head potential because it looks like a Mexican head. You can see here that there's not only two minima, but a whole circle of minima. So this is a bit more complicated now. So let's see how the field behaves with this circle of minima. So let's take a closer look at the Mexican head potential here again. And for simplicity, we assume now that there are only 4 different points of the circle which are occupied after the phase transition. Let's denote the different areas of the circle by values of pi, right? So we can start here with 0, then we have pi half, here we have pi, and here 3 pi halves. So then again, like in the examples before, patches which are close to each other, they will have the same value. So you can see here one patch where it settles at 0, one patch where it settles at pi, and so on. And the nice thing is, between these patches, you can interpolate continuously because you can just walk along this minima circle. So you can just walk from here to here, from here to here. So there's no need for going over the maximum. So there are no domain walls. However, if you look closer to these 4 patches here, there's something interesting going on. So you have first 0, then it goes continuously along the circle to pi half, to pi, to 3 pi half. So it's one circle, and you can make the circle smaller and smaller and smaller and smaller, until at one point, there's only one single point left. And for crossing this single point, you have to jump over the maximum. So here you have like a point-like defect. And this is called a cosmic string. Now you might wonder, string, point-like defect, how does this add up? It's because this is only a 2-dimensional representation of our space. Of course, we have 3 dimensions. So this is not quite accurate yet. So when we try to expand it to 3 dimensions, it looks in the following way. Now we have the same here, the Mexican head potential. And now let's represent it by different colors. So the potential can settle for color red, green, or blue. You can see here the different patches. And here you can see that we can interpolate continuously. Is this one this? Like with colors, you can go continuously from red to green and from green to blue and so on. So only here you have this point-like defect in the middle. But then since it's just one 2-dimensional plane in the 3-dimensional space, you can put a lot of these disks on top of each other for achieving a 3-dimensional space. And then you get this picture here. So you have here this, and all these point-like defects, they combine to one string. So this is how you get the cosmic string. It's, I hope, so far straightforward. Before we go on about how to do research about them and how to find out more about them, let's have a quick summary about what you have learned so far. So we start by the universe is expanding. This leads to a drop in temperature, which then changes the shape of the potential. We now have patches of the universe, different patches that settle at different minima of the new potential. Then the neighboring regions within the same patch, they have similar phi values due to the continuous interpolation. But between those different patches, phi must jump over the maximum. So here, in those intermediate regions, we have higher energy density, and this leads to the formation of topological units. Okay, so how do we find out more about them? Because for now it's pretty abstract, right? So we have basically 2 different approaches in our team. There are also more different approaches, but we use these 2. So there's the analytic approach, which is the velocity-dependent one-scale model, which was in fact the topic of the PhD thesis of your professor, Carlos Martins. And the numeric approach, pure theory simulations. I will focus on the field theory simulations because that's what I'm working with right now, and later we will go to the analytic approach. So since for most people it's not quite clear what numerical simulations are, I try to give you a very quick overview about what this is. Let's start with the example of two planets. So you can have two different planets, different masses, and they orbit each other. And we can find out exactly how they orbit each other by solving the Kepler equations. So this means we know for the future always where they will be. However, as soon as we add a third planet, it's not possible anymore to solve it analytically. So this means now we need numerical simulations for computing the time evolution. How do we do this? So in the example of this three-body problem, we start by defining the location of the particles, which in this case is the planets. Then we calculate all the forces that result in the change of the location. So in this case, it's the gravitational forces. And we update the locations for small time steps. So this means we compute the equation of motion, and then we repeat. So this means if you want to know where the planets are after 100 time steps, you have to repeat this 100 times. So as you might already guess, it's very, very, very cumbersome. So we do it on a computer, obviously. And in our case, it is a bit different since we are working with fields. So here we don't start by defining locations of particles, but we start by defining a lattice. So a lattice can be just a representation of the space. So for example, again, in this auditorium, we have a lot of chairs which are equally spaced, and there's a certain number of columns and a certain number of rows. So they can define our lattice. And then for every lattice point, which means every chair in this classroom, we define a field value phi. And then we update the field value according to the equations of motion for a very small time step. And then we repeat. So this means for every single chair or every single lattice point, we have to do this equation for a small time step, and then do it again and again and again, which of course is very computationally expensive, right? So how exactly do we do this for the domain wall case? We use this equation of motion, and no worries, you don't have to understand this equation. I just want you to see what are the dependencies of this equation. So you have the field phi, and you have the conformal time eta. So you have the derivatives here according to eta, and also you have the potential here with the derivative to phi. Then you also have the scale factor A here, and you have the, and that's it. So you have all these things which are part of the equation, and then you can evolve in time. Now this is, for example, how a snapshot of one of these simulations looks like. So we have a lattice with 2048 columns and 2048 rows. So it's a very big lattice. So basically in this picture here, it's every single pixel that you can see. For every single pixel, we have to do this calculation. We start by, in the beginning, just distributing phi uniformly, randomly between the two minima. And then we just wait and see where it will settle. So obviously, so we expect it to settle in the two minima, right? And we can see here, so the different colors here represent the values of phi. So red means that phi is at +1, which is here defined to be the positive minimum. And blue is at -1, which is the negative minimum. So you see that we have different patches with different minima. Here you can see it even bigger after more time has elapsed. And the regions between this, so the borders, that's where the domain walls are. For cosmic strings, I can also show you a picture without explaining too much about it, because it looks cool. So this is a three-dimensional snapshot of a cosmic string simulation. And here you cannot just plot the phi values, but it's, for example, possible to just plot the values which have a high energy density, and then you can get these nice strings. However, as you might have already guessed from how I explained the numerical simulations, the problem with them is that they are limited due to computational resources and time. So this means we cannot evolve the whole lattice for such a long time that we know what we would expect nowadays to see in the universe. right now we are working with the Leonardo cluster. It's a supercomputer in Italy, and it's the second fastest supercomputer of the whole of Europe. And even this one is not, it's not possible with that one even. So this means we need the analytic approach for longer time evolutions. So let's see what this analytic approach does. The basic idea here is to start from statistical physics and turn it into thermodynamics. What does this mean? We take the microphysics given by the Nambu-Goto action. This is exactly what I showed you before in the equation. So this is this small update of every single lattice point. These kind of equations we take, and then we average over the whole network, where we then obtain the evolution equations for the macroscopic quantities, like, for example, the average velocity of the defects or the average density of the defects. So this means in the end, with these kind of equations here, we don't know where exactly a domain wall is or where a string is, but we know how many there are comparative to the whole lattice. So this is already quite nice. However, there's a problem also. There are some unknowns that are remaining while obtaining the equations of motion. So that's, of course, a problem. And this means we need our numerical simulations for providing a calibration for the analytic model. So this means we need both for doing a very long time evolution. So first we have the numerical simulations, then we calibrate the analytic model. Yeah, and when doing this, finally, one can explore observational consequences. I didn't do this so far, but of course people are doing it. Because topological defects are regions of concentrated energy, so we expect observational footprints in the stochastic gravitational wave background, like Beatrice was already mentioning in her talk, and also in the cosmic microwave background. And then in the end, we can compare our results to observations, and this might allow to tighten constraints on the theoretical paradigms, so the theoretical models for this theory. So finally, we hope, so far, cosmic strings and domain walls have not been observed. We hope that in the future, with the next telescopes which have a higher precision, it might be possible. And then, in the end, hopefully, domain walls and cosmic strings will prove to be useful fossils and enable us to learn more and more about the history of the early universe. Thank you for your attention and feel free to ask.